Hello everyone, this is Gordon. We're back with a second set of problems on friction. The first one, a bowling ball with an initial velocity of 3 meters per second rolls along a level floor at 50 meters before coming to a stop. Find the coefficient of kinetic friction. So writing down our variables, we have v sub 0 is equal to 3 meters per second. The distance traveled, 50 meters, and again we're finding mu sub k. And so drawing the picture, we have a ball on a level floor with a weight, which is equal to mass times the gravitational constant, the force that opposes that, the normal force, and the only force parallel to the plane in which the ball is moving, the frictional force, the force that's slowing the ball down. And that, of course, is equal to, according to Newton's second law, mass times acceleration. And so using F sub F is equal to mu sub k, we have mass times acceleration is equal to the coefficient of kinetic friction times normal force, which is mu mg, and so we have the relationship coefficient of kinetic friction is equal to the deceleration of the ball divided by the gravitational constant. What is A? From an earlier set, A is equal to v sub 0 squared times 2 times the distance the ball travels, and so we substitute numbers. 3 meters per second squared divided by 2 times 50 meters. Acceleration then, or the deceleration of the ball, 0.09 meters per second. And then we have mu sub k is equal to, thank you very much, second squared, 0.09 meters per second squared divided by the gravitational constant, 9.8 meters per second squared, giving us a numerical value for mu sub k of 0.0092. And that's the first problem. The second problem, if the coefficient of kinetic friction between a rubber tire and a wet concrete road is 0.5, how long will it take for a car with an initial velocity of 30 kilometers per hour to stop? How far does it go? Writing down our knowns, we have mu sub k is equal to 0.05, v sub 0 is equal to 30 kilometers per hour. We're looking for a time, and we're looking for a distance. And I recall from last problem, we had a relationship between deceleration and gravitational constant, and I know that there are relationships between acceleration, velocity, and time, and so I'm going to look for the acceleration, use the v sub 0 given, and come up with the time, and from that I can get a distance. Drawing the picture, the car with the weight and the opposing normal force, the frictional force that's retarding it. As before, we have F sub F is equal to the coefficient of kinetic friction times the normal force, which is equal to mass times acceleration, which allows us to say that the acceleration is equal to 0.05 times 9.8 meters per second squared, giving us a numerical value of 4.9 meters per second squared for the deceleration of the car. And since velocity or acceleration is equal to velocity times time, we rewrite that. Velocity is equal to, or time is equal to, velocity divided by acceleration. Using the conversion factor I gave earlier on the first set, we have 8.33 meters per second divided by the deceleration that we just determined, 9.4 meters per second squared, giving us a time in which the car stopped of 1.7 seconds. And it's that time that we'll use in the second half of the problem to determine how far the car traveled during that time period. From an earlier set of problems, we have distance traveled is equal to v sub 0 t plus 1/2 at squared. Using the numbers that were given and the numbers that we determined, we have 8.33 meters per second times 1.7 seconds plus 1/2 4.9 meters per second squared times 1.7 seconds squared, giving us a numerical value of the distance traveled by the car during that time, 21.25 meters. And that's problem number 2. Problem number 3, a machine on a wooden skid is to be slid down a pair of planks off the back of a truck. If the coefficient of static friction is 0.28, what angle should the plane make so the machine slides at a constant velocity? Will it slide down without a push? We have from the first set of problems a relationship between mu sub s and the angle. Since we're using constant velocity here, taking a look at the picture, F sub F, the frictional force, is going to equal the force down the plane, and that will allow us to use that relationship. We know that the mu sub s, the relationship mu sub s and theta will hold, and so given that mu sub s is equal to the tangent of the angle of repose is actually what it's called, the angle of repose, then we have 0.28 is equal to tan theta. And finding the inverse tangent, we have theta is equal to 15.6 degrees. Will it slide down without a push? Given that the forces are equal, nope, it's not going to. It's going to need a push to get started. And our final problem, problem number 4, a truck moving at 100 kilometers per hour carries a steel girder resting on the floor. We're asked to find the minimum time at constant deceleration in which the truck can come to a stop without the girder moving. How fast can you slow down without losing the load? And so we're using a coefficient of static friction, 0.5. The known velocity, initial velocity, 100 kilometers per hour. And we're asked to find the time, and we know that mu sub s can give us a relationship between deceleration and the gravitational constant. Drawing the picture, the girder on the floor of the truck with a weight equal to mass times gravity, and the opposing normal force, and the frictional force, which is what the static frictional force, which is what's keeping it in place. And so as before, F sub F is equal to mass times acceleration, which is equal to mu sub S times n, which is equal again to mu sub S times mg. So acceleration, or the deceleration, is equal to mu sub S times g, 0.5 times 9.8 meters per second squared, or 4.9 meters per second squared. Then, since acceleration, we have a relationship between acceleration, velocity, and time. Since v is equal to a times t, the time is equal to velocity divided by the acceleration. The velocity is given as 100 kilometers per hour using the conversion factor. That's 27.7 meters per second. We divide that by the deceleration that we found, 4.9 meters per second squared, and come up with a time of 5.7 seconds. And that's the end of the fourth problem and the end of the set. Thanks for watching.